Delaware Tech, Chemistry 100, Chemistry 110, Unit 5 continued, reaction types. So there are 6 main reaction types, but if you look at all the chemical reactions out there, there are literally millions of different chemical reactions, and nobody can remember all of them. So chemists have categorized these into 6 main categories of reaction types. And nearly all reactions can be fit into one, sometimes two of these reaction types. So we have combination. This is the first one. And a combination, also known as synthesis, is very easy to spot. If you start with more than one reactant and you end up with exactly one product, that's a combination reaction. You have combined reactants to form a product. Decomposition is exactly the opposite. You start with one reactant and you break it down into 2 or more products. So those two are essentially the opposite of each other. Those are the first 2 categories. Then we have what's called a single replacement, sometimes known as a single displacement reaction. And here we can recognize this because it will be some element, and it'll be an elemental form of something. So it could be a single atom element or a diatomic element, but some elemental form, so it's only made of one kind of atom, will react with a compound that's obviously by definition made of a couple different kinds of atoms. And the product will be a new compound and a new element that was derived from the first compound. So you're going to look for that pattern of element plus compound makes a new compound and a new element. And it's very easy to spot that way. Double replacement, this is where you're starting with 2 compounds and you end up with 2 brand new compounds. And these compounds are typically ionic compounds made with a cation and an anion, or more than one cation and more than one anion. And essentially they swap partners. So the first one's cation will bind to the second one's anion and vice versa, making 2 completely new products, new compounds. And this one will always have compounds reacting with compounds to produce 2 new compounds. The 5th type of reaction is called combustion. We've already mentioned this briefly. That combustion can mean a lot of things, but for these classes, for Chem 100 and Chem 110, we're going to limit our definition of combustion to just carbon-based compounds that are reacting with O2, oxygen gas, and the only products that we will form are carbon dioxide and water. So you're going to look for a carbon compound reacting with oxygen to produce CO2 and water. Now I'll tell you, there are some chemical reactions that also produce carbon dioxide and water that are not combustion reactions. So you must look for the carbon compound, carbon-containing compound, reacting with oxygen as your tip-off that this is a combustion reaction. And the 6th reaction is called oxidation reduction. For short, we refer to it as redox. We take red from reduction and ox from oxidation. We squish those 2 together and we refer to it as redox reactions. And these are reactions where you're changing the charges on different atoms or the oxidation states. The oxidation state is the more proper term for the charge on atoms because some atoms have formal charges like ions that we've already talked about, but you can even have oxidation states of atoms that don't have actual charges to them, but they have a certain state that's related to how many valence electrons they have. So oxidation reduction reactions are a little different from the others in that the first 5 reactions, it's one of those 5. If it's one of those 5, it's only one of those 5, and it can't be another one of those 5. However, many of those first 5 can also be oxidation reduction reactions. Some combinations can be, some decompositions can be, all single replacements and all combustions are redox reactions. But if you're asked for which is the main category for this reaction, you're going to look for the clues we just talked about. And we'll go over each of these reactions individually. So you recognize them by the pattern of reactants and products. And I've already mentioned that the E stands for elements, the C stands for compound in the case of the 2 replacement reactions. And sometimes when we see these patterns, we can predict what the products will be. which is nice. If we have a new reaction or reacting two products, and we can actually make guesses as to, two reactants that are reacting together to make new products, we can actually predict what those new products are in many cases. So let's talk about the first reaction, combination reaction, also known as synthesis. You're combining reactants, some reactant A with some reactant B, to make a linked compound as a product. So there's only one product formed. Now you might have two molecules of that or two formula units of that, but there is only one new compound, one product total. And that's what tells you it's a combination reaction. So you can think of it as Homer sees a donut, and they combine together to become Homer donut. So you get a lot of binary compounds by doing this because you're taking two separate elements sometimes. Some of these reactions involve two separate elements. Some of them involve two separate compounds that are binding together, and some involve an element and a compound. So don't just look at the reactants. You have to also look at the products to determine whether this is a combination reaction. So here's an example of an elemental form of sodium with the elemental form of chlorine gas, Cl2, forming sodium chloride, one product. One product is your tip-off. It's a combination. You can also have hydrogen gas and oxygen gas mixing together, reacting to become water, one product. Aluminum, when it's burned in the presence of oxygen, becomes aluminum oxide, one product. So these are all examples of combination reactions where both reactants are elements. But we have, and here's another one, magnesium and nitrogen gas. We've already talked about this one to make magnesium nitride. But we also have combinations where we're mixing elements and compounds together, or compounds and compounds. So here are a few examples of compounds plus compounds. H2O with the SO3 gas to make H2SO4. That's sulfuric acid, and that's a combination reaction. You'll notice both of the reactants are compounds. They're not elements. Ammonia, NH3 plus HCl makes ammonium chloride, a single product in this case. Carbon dioxide and water can combine to form H2CO3 in water, which we call carbonic acid. And by the way, this reaction can go backwards. In fact, many of these reactions under the right conditions can go backwards to become decomposition reactions. So the one product is your big tip-off that it's a combination reaction. The second you see just one product, you know what it is. Decomposition is the exact opposite. Decompose means to break apart, to fall apart. You're starting with some single reactant and making two or more products. And the products can be elements, the products can be compounds, just like you saw in the previous example going the other way around. So an example would be you have a couple, and the couple breaks up into its individual partners of the couple, and that would be a decomposition reaction in real life. So you can have that happening with binary compounds that are only made of two kinds of elements, and they typically will break apart under the right conditions. In this case, you need electricity to break apart sodium chloride. This is the sodium chloride that's table salt, but this reaction only goes at very high temperatures with electricity. You have to have very high temperatures to melt the sodium chloride, and then once you pass electricity through it, you can make this reaction go in the backwards direction that we saw previously to produce sodium metal and chlorine gas. You can do the same thing with water. If you put electricity in water, it will break water down into hydrogen gas and oxygen gas. Mercury oxide, if you heat it up high enough, it will break up into mercury, which is a liquid metal, and oxygen gas. So they separate. So those are all examples where the products are both elements. But that is not your tip-off. Your tip-off is that you're starting with one reactant. Because you also have examples where you're starting with ternary compounds. These are compounds that have three or more elements in them. Calcium carbonate. If you heat it up, you don't get calcium and carbon and oxygen. You get carbon dioxide and calcium oxide. And there's no way for you to predict what the products are in this case. If you see a ternary compound that is decomposing, you really have to be told what one of the two products is. Like if I told you CO2, you would literally subtract the CO2 from the CaCO3, and that would tell you, oh, you have one calcium left and one additional oxygen left, and that will be your second product. And likewise, nickel carbonate does the same thing. You produce CO2, and what's remaining is nickel 2 oxide, NiO. And carbonic acid that I showed you in the last time can also go backwards. Remember, we formed carbonic acid from CO2 and water. Well, this reaction freely goes back and forth, so you can also drive carbonic acid to form CO2 and water. Now notice the products are CO2 and water, and I just finished telling you that combustion reactions always produce CO2 and water, but this is not a combustion reaction. So you have to be careful what you're looking at. There is no burning with an oxygen atmosphere here. You're not adding oxygen to the starting material and setting it on fire to make CO2 and water. You're merely taking a single compound and breaking it down into two compounds, and that tells you it is a decomposition, not a combustion reaction. Single replacement reactions. So here you have one type of atom swaps places with another of a similar type typically. So you can envision that you have some element A reacting with a compound we'll call BC, and then B breaks its bond with C and forms a new bond with A, leaving C alone. So C is the new element and AB is the new compound. And this would be as if you had Marge here and then Homer Pig interact, and Marge takes her husband back and the pig is left by himself. So you have Marge, the element Marge, and the compound Homer Pig making the new compound Homer Marge and the new element the pig. And so examples of that might be sodium plus potassium bromide reacting. And this reaction, it can be quite violent, by the way, so you have to be very careful. But the two metals, the things that are alike, will swap places. Typically, cations, the potassium in this case is your cation, will swap place with something that can form a cation, the sodium. And then you end up releasing potassium metal, the K metal, and forming NaBr, a new compound. Here's an example where you have fluorine gas reacting with lithium chloride. So fluorine is a halogen. It's an elemental form of a halogen, and it's reacting with this salt that's made of lithium and chloride. Lithium ion and chloride ion. Well, chlorine and fluorine are both halogens, so the halogens will swap places. The lithium will no longer be bound to the chlorine. It will bind to the more reactive fluorine, forming lithium fluoride, LiF, leaving behind chloride, but the chloride will bind with another chlorine to form chlorine gas. There's another reaction going on here. It's a little more advanced, but suffice it to say, likes will swap places with likes. The halogens will swap with halogens. Metals will tend to swap with metals. Here's another example of halogens swapping with halogens. You have chlorine gas and sodium bromide. So this is very similar to the second reaction. The chlorine and the bromine will swap places, and you'll end up with sodium chloride and bromine as your product. Bromine's a liquid, but in this case it's dissolved in water. You can also have metals swapping places with hydrogen. So hydrogen frequently will form cations in compounds, much more than it forms anions. You've learned that hydrogen can form H plus cation, but it can also form H minus hydride anion. But the vast majority of reactions with hydrogen involve cations formation or cation usage. So in this case, the hydrogen in HCl is a cation that will swap places with zinc, which can form a cation. So anytime you see zinc and an H on another molecule, that other molecule is probably an acid, and in this case, this HCl is hydrochloric acid. The zinc and the H will swap places. You'll end up with zinc with the chlorine instead, and hydrogen by itself. Remember, you have to, when you're forming a new element, the element will be produced as its own elemental form. So in the first reaction, the elemental form of potassium is just K. The elemental form of chlorine is chlorine gas, Cl2. Of bromine, it's bromine liquid, Br2. And of hydrogen, it's hydrogen gas, H2. So you have to be aware of the elemental forms of each element. Metals will always be by themselves. Noble gases will always be by themselves. But many non-metals, especially the halogens and the other gens, hydrogen, oxygen, nitrogen, will become diatomic. And you need to be aware of that. In the meanwhile, the zinc will find the chloride, and you have to use crisscross and simplify rules to realize that the product will not just be a zinc with one chlorine, it'll be a zinc with two chlorines. So you need to do crisscross simplify. You need to know the zinc will form +2. That's the only cation zinc forms. The chloride is by definition -1. When you crisscross, you get zinc ZnCl2 for your formula. And it's important to know what the product formulas are, because otherwise you won't be able to properly balance the equation when you're done writing the skeleton equation. Here's another one. Calcium metal in water will react to form calcium hydroxide plus hydrogen gas. So the water will actually break apart into OH minus, which will go with the calcium, and H plus, which will actually change from H plus to H atoms and become H2 gas. Now, I'm not going to go over the details of the H changing, but suffice it to say, if you're producing H by itself, it will find a way to produce the elemental form in many cases. So in this case, we have a single replacement. The calcium is swapping places with one of the hydrogens. So whenever you see water in a chemical reaction, frequently you want to think of the water as hydrogen. Hydrogen. It's a little hard to write this. I'm setting off my little detector. I'm going to delete that and write it over here. Hydrogen linked to OH. So it's best to think of water this way, and you can even think of it as H plus and OH minus, the hydroxide. So many reactions will split the water this way, and the OH minus will go with the calcium, and the H plus will find another H plus, and it will eventually become H2 in the process. So a double replacement is where you have two cations and two anions. So you have a cation-anion pair, and you have another cation-anion pair, and the cations swap with each other, and the anions switch with each other. So you end up with the cation, the first cation bound to the second anion, and the first anion bound to the second cation. So it's two couples swapping partners. So you start with two compounds, you end up with two brand new compounds. You can think of it as the Flintstone couple and the Rubble couple swap partners, and now Fred is with Betty and Barney is with Wilma. So that would be a double replacement reaction. So typically this is done with two ionic compounds, or an ionic compound and an acid, because the acid will behave like an ionic compound. It will break apart into ions in water. So this is usually done in aqueous solution, meaning in water. The negatives will swap with the negatives, the positives will swap with the positives. And here's an example. Sodium hydroxide and iron 3 chloride. The sodium and the iron are your cations. This is sodium plus, and this is iron plus 3. And they will switch places with their respective anions. So now you have iron with the hydroxide and sodium with the chloride. But now, to know what the actual products are, it is very important that you do the crisscross simplify to figure out your final formulas. So this tells you, remember, put a parentheses around your polyatomic. This tells you that you need one iron, but you need 3 hydroxys, and we don't bother writing the 1, of course. And then your other product will be sodium 1, chlorine 1, and of course we don't write those numbers either. So our actual products will be Fe with 3 hydroxides and NaCl, and I'll just show you that written on the next line. So you have to be aware that you need to figure out the formula of the products using crisscross simplify. So here's another example, potassium chloride with copper 2 sulfate makes copper 2 chloride and potassium sulfate. So the sulfate and the chlorine or chloride swap places, and the copper and the potassium swap places to make these 2 new compounds. And again, each time you have to do the crisscross simplify. For example, with the potassium, we know we have a K plus, and the sulfate, it is best to put it in parentheses and remind yourself it has a -2 charge and that this is +1, and now you crisscross, the 2 goes there, the 1 goes here, and you end up with this compound. Likewise, with the copper, you know you're starting with copper +2 because that's what it was here, and you have chloride, which is -1, again, crisscross and simplify, and you end up with CuCl2. So I'm going to erase that. You also have sulfuric acid, H2SO4, reacts with sodium hydroxide. And in this case, the sulfate of sulfuric acid will break up by itself, so you'll have 1 ion of sulfate, and you'll have 2 positively charged hydrogen ions. In the meanwhile, you will have, and actually I just realized this should say 2 right here. That's 2 sodium hydroxides. And you have 2 sodiums over here, 2 sodium ions, and 2 hydroxide ions that you're starting with. And what happens is these 2 protons, H pluses, we call them protons, we'll describe that later in acids and bases, but the 2 hydrogen ions will find the 2 OH minus ions to form 2 new waters, and the remaining sulfate will bind with the 2 sodiums to make sodium sulfate. And I'm going to clear these notes here, but I will rewrite the 2 because that was mistakenly left out. So one more example, here's ammonium sulfate. So ammonium is your cation, sulfate is your anion, and it's reacting with barium fluoride. Barium is your cation, fluoride is your anion. They swap partners, and you now have a product of barium sulfate, and you have enough to make 2 ammonium fluoride products. So get used to swapping these partners out. I'm going to leave that there for now, and we'll actually clear that to move to the next slide. And so let's talk about the double replacement reactions. When you're actually doing double replacement reactions, there are a couple things that will tell you the reaction actually occurred, because sometimes you can't tell that ions have swapped partners just by looking at a tube of a chemical reaction that looks clear before and after. So there are some things that will tip you off that a reaction actually occurred, that the swap of ions occurred. One is that you form a new compound with a new cation and anion pair that's not soluble in water, and you'll actually see precipitate form at the bottom of your solution. You'll see these solid crystals drop out of solution, precipitate and form a layer on the bottom. It might be a white layer in the case of calcium sulfate. It might be a yellow layer in the case of the lead 2 iodide that's shown here as well. Zinc hydroxide is another one that's insoluble when you form it. Another big tip-off is sometimes, as I just showed you in the last example, sometimes the H plus from one molecule, usually from an acid, will react with the OH minus of a second molecule, usually a base, and then these 2 will find each other to form HOH, which is just another way of saying H2O. And I showed you that in the last example when I had H2SO4 reacting, I forget which compound it was, but I think it was sodium hydroxide, yes. So you need 2 sodium hydroxides here, and so you have 2 hydroxides and 2 H pluses, and they find each other to make 2 waters, plus the remaining sodium sulfate. And the tip-off here, you don't really see waters forming. You can't see waters forming in water. However, this reaction of forming water from a positively charged H plus and a negatively charged OH minus is a very, very favorable reaction and will actually generate heat. So you can actually feel the temperature of your test tube go up. You can always test it by putting a thermometer in when you do the reaction and watch the temperature of your reaction go up. So that's your tip-off that water is formed. It doesn't always tell you it's water, but it frequently does if you're starting with an acid and a base reacting to form water and some other salt, some other ionic compound. And then the third way, which doesn't happen a lot in double replacements, it actually happens much more frequently in single replacements, is you'll see bubbles formed because some gas is being produced. That could be carbon dioxide gas, that could be sulfur dioxide gas, or it can even be H2 gas, hydrogen gas. You don't usually see hydrogen gas in any examples of double replacements because hydrogen gas is an element and you won't find an element product in a double replacement. So I didn't write it here, but H2 is also produced especially in single replacement reactions where a metal is replacing a hydrogen in a molecule. So here's some double replacement reactions, also known as double displacement. We're going to write the products. We're going to figure out the formulas of the products, and then we're going to balance the equations. So we have calcium chloride and sodium hydroxide. Well, here's your anion here. It's -1. And here's your anion here. Each chlorine is a -1. We have 2 of them. The calcium is +2. The sodium is +1. And they're going to swap partners to form calcium hydroxide that has 2 hydroxides because you have to do crisscross simplify, and sodium chloride. And now it's a matter of, once you know the right formulas, then you can balance the equation using the rules we talked about the last time, and you see that you need 2 sodium hydroxides, and you will produce 2 sodium chlorides, and everything else is 1 of that formula unit. The next reaction is copper 2 chloride with lithium sulfide. So the chloride and the sulfide are your anions. They'll swap places. The metals, the copper and the lithium, will swap places, and you end up with copper 2 sulfide. And how do you know it's this formula? Well, the copper was +2. The sulfide is always -2. You crisscross. So if you were figuring out the formula, you would initially say, oh, it's Cu2S2, but you know you can simplify this to just 1 of each, and we would write it this way. And lithium chloride is obvious because lithium is +1 and chloride is -1, so that's your product. And now you balance the reaction. The next one is calcium hydroxide, so treat the hydroxide as a single unit. It will move together. And you have nitrate over here. You have iron 3 nitrate. And the iron 3 will swap with the potassium. The hydroxide will switch with the nitrate. And now the potassium will get 1 nitrate. The iron will get 3 hydroxides. Remember, crisscross simplify. And then you balance the equation. The next example is ammonium sulfate, and ammonium is your cation. Each ammonium is +1, each sulfate is -2. Put parentheses if that helps you realize that. Each barium is +2, and each fluorine is -1. It's really one of those fluorines is -1. And now you swap partners. So the ammonium will be bound with 1 fluorine, 1 fluoride, and the barium will be bound with the sulfate. Remember, the barium was +2. The sulfate was -2. When you crisscross, you get 2 and 2. When you simplify, you get 1 and 1. And therefore, these would be your products. And the last example is magnesium bromide and sodium phosphate. And this one might be a little trickier to figure out the products. Because magnesium is +2, sodium is +1, bromine is -1, but phosphate is -3, and we have 1 phosphate group here, so don't confuse that. So when you mix the magnesium with the phosphate, You know the magnesium has a +2. You know the phosphate's a -3. So the 3 will go here as it's already written, and the 2 will go here as it's already written. And that's where these numbers come from. And there's no need to simplify that. That's as simple as you can get. So you end up with these products, and then you can balance the equation. And you'll notice the final balanced equation has 3 magnesium bromides plus 2 sodium phosphates makes 6 sodium bromides and 1 magnesium phosphate.